Mastering Pandas, Series and DataFrames. In this lesson, we will dive into Pandas series and DataFrames. You will learn how to explore, clean, filter, and analyze real-world data. Let us start our Pandas journey. Running the cell now. Let us ensure our notebook stays free of distracting warning messages. We import the warnings library. Import numpy as np. We set the random seed to 42 for reproducibility. We tell Python to ignore warning messages so the output stays clean. Running the cell now. This cell sets up the environment by importing necessary libraries and configuring options to suppress warnings for cleaner output. While there's no visible output, notice that initializing the random seed ensures reproducible results in data operations and analysis later in the lesson. This prepares us to confidently explore and manipulate Pandas series and DataFrames with consistent behavior. If you are ready, let us begin exploring data. We need data to practice. Let us load the Titanic dataset, a classic for data analysis. We use a comment to describe our block, data setup with the Titanic dataset. We import Pandas. This is the main library for data analysis in Python. We provide the direct URL to the Titanic dataset. We load the CSV file into a DataFrame named df. We print the shape so we know how many rows and columns we have. We show the first 3 rows to preview the data and check the columns. Running the cell now. This output confirms the Titanic dataset contains 891 rows and 12 columns, showing key passenger details like survival status, class, and fare. Noticing these columns and their values helps us understand the structure of the data frame, which is crucial for effective data exploration and filtering in Pandas. This step lays the foundation for analyzing real-world data by first inspecting its shape and head entries. Try loading a different dataset you are interested in. What is a Pandas series? A Pandas series is like one column from a spreadsheet. It holds data values and an index, which is like row labels. Running the cell now. Let us build a basic Pandas series so you see how it works. This comment tells us that we are creating a series. We import Pandas again for completeness. In real code, we do this only once, but it is harmless here. We create a series called ages holding for simple numbers. We print the series to see how Pandas displays it. Running the cell now. This output shows a Pandas series with 4 numeric values, each automatically assigned a default integer index from 0 to 3. Notice how the series resembles a single spreadsheet column, with the index serving as row labels, which helps identify each element's position. This demonstrates the fundamental structure of a series as explained in this lesson section. Create your own series with your favorite numbers. Now let us look at how to turn a DataFrame column into a series. This comment indicates we are selecting a column from our DataFrame. We extract the survived column from the Titanic data as a series. We print the type to confirm it is a series. We preview the top rows of this series to see the output. Running the cell now. This output shows that selecting a single column from a data frame returns a Pandas series, confirmed by the printed type. The series displays the first 5 values of the survived column along with their integer labels, the index, illustrating how a series combines data values with an index. This reinforces the lesson that a series is essentially one column of data with labeled rows. Try selecting other columns as series. What is a data frame? A data frame is like an entire spreadsheet, with rows and columns. Each column is a series. The data frame lets you work with all of them together. Running the cell now. Let us learn how to get a summary of our data frame fast. This comment notes that we are checking our data frame's info. We display information about each column, like data type and missing values. Running the cell now. This output shows the structure of the data frame, including the number of rows, 891, and columns, 12, along with data types and non-null counts for each column. Notice how some columns, like age and a cabin, have missing values, highlighting the importance of handling incomplete data. This helps us understand the overall shape and data quality before further analysis. Knowing the type of data helps you plan your analysis. To understand our data, let us look at some statistics across columns. This shows we will get summary statistics for the data frame. We get mean, minute, max, and more, for any numeric columns, at a glance. Running the cell now. This output summarizes key statistics for each numeric column in the data frame, such as counts, means, and ranges. Notice how it gives a quick snapshot of the data's size, e.g., 891 rows, and variation, like the wide range in passenger ages and fares. This helps us understand the overall structure and content of the data frame when working with all columns together. Check these stats whenever you start with new data. Let us find out what columns our data frame has and its overall shape. This is a comment describing that we'll view the data frame's columns and shape. We print the column names as a list to understand the features available in the data frame. We print the shape of the data frame, showing the number of rows and columns it contains. Running the cell now. Here, the output shows the data frame has 891 rows and 12 columns, with each column named clearly. This confirms the data frame holds multiple related columns, like a spreadsheet, and sets us up to explore the data by working with these columns collectively. Cleaning data, handling missing values. Often, real-world data is messy. Let us check for missing values in our Titanic dataset. Running the cell now. We should always look for missing values early in any data science project. This explains that we are about to check for missing values. We print the total missing entries in each column. Running the cell now. This output shows the count of missing values in each column of the Titanic dataset. Notice that the aged column has 177 missing entries, cabin has a large number with 687 missing, and the embarked has 2 missing values, indicating these columns need cleaning before analysis. Identifying these gaps is crucial to handling missing data effectively in the next steps. Do you spot columns with lots of missing data? Let us fill missing values in the age column using the mean. This helps preserve the data while minimizing bias. We add a comment to show our intent, fill missing age values with the average age. We use fillna to replace missing ages with the overall average. Running the cell now. This code replaces missing age values with the dataset's average age, ensuring no gaps remain in this important column. Although no output is displayed, this step is crucial for maintaining consistent data quality before analysis, preventing errors or biases caused by missing values. Notice how filling missing data helps us work with a complete and reliable dataset. Try filling missing values with median or a constant instead. Sometimes it makes sense to drop rows if missing values are rare. Let us do that for embarked. We explain that we are dropping rows with missing embarked. We remove any row from our data where embarked is missing. Running the cell now. After running this code, any rows where the embarked column had missing values are removed from the dataset. This ensures our analysis only includes passengers with known embarkation points, improving data quality. Notice that no output appears because the change is made directly to the data frame, reflecting our intent to clean the data by handling missing values. Now let us use condition-based filtering. We will select all child passengers. This comment mentions we will find passengers younger than 18. We create a new data frame called Kids with passengers under 18. We print their names, ages, and genders for a sample. Running the cell now. This output shows the first few passengers under 18 from the Titanic dataset, highlighting their name, age, and sex columns. Notice the ages range from 2 to 14, confirming the filter condition worked correctly. This step helps us focus on a specific subgroup and assess if missing values in the age column might affect our analysis of young passengers. Use filters to discover interesting groups in your data. Let us try combining multiple filter conditions. We want women in first class who survived. We show that filters can be combined using Boolean logic. We find all rows where the passenger is female, in first class, and survived. We print names and ages so we can see a sample. Running the cell now. This output shows the first few entries of women in first class who survived the Titanic disaster, with their names and ages. Notice that some ages, like for Spencer, Mrs. William Augustus, are missing and filled with a placeholder, 29.699118, highlighting the data cleaning need to handle such missing values properly. This step helps us identify where missing data exists before deciding how to impute or remove it in our cleaning process. Try modifying the filters for practice. It is helpful to see how survival rates change by ticket class. Groupby helps us summarize data. This block shows how to calculate the average survival by passenger class. We group data by class, then show the mean value in the survived column for each class. Running the cell now. This output shows the average survival rates grouped by passenger class, revealing that first-class passengers had the highest survival likelihood, followed by second and third class. Notice how this grouping helps identify key trends despite any missing data, underlining the importance of handling missing values to ensure accurate insights. What else might you group by? We can aggregate more than one statistic at a time. Let us look at the mean, minimum, and maximum fare by embarkation port. Aggregating makes comparison simple. Running the cell now. This output shows the average, minimum, and maximum fare paid by passengers grouped by their embarkation port, C, Q, S. Notice how the mean fare for port C is much higher, with a wider range, indicating different passenger classes or ticket types. This helps us understand the distribution of fare values and can guide how we handle missing or inconsistent fare data later in cleaning. Let us take a look at how often each value appears in categorical columns. This line is a comment indicating that the following code will show value counts for categorical columns. This line prints the count of each unique value in the datasets column of the data frame. This line prints the count of each unique value in the embarked column of the data frame. Running the cell now. Here, the value counts reveal the distribution of passengers by a sex and the embarked port. Notice how there are significantly more males than females, and est is the most common embarkation point. This helps us identify if any categories have unexpected missing values or imbalances before we decide how to handle them. Try value_counts on other columns like P-class. Let us add more detail by mapping codes to real port names. This makes data more readable. This comment explains that we are adding readable port names to the embarked codes. Here we create a dictionary that maps each embarked code to its full port name. We create a new column port in the data frame by replacing codes with their port names using the dictionary. We print each unique combination of embarked code and port name to verify the mapping. Running the cell now. Here, we map the abbreviated port codes in the embarked column to full port names, creating a new porter column. This output shows the unique mappings, confirming that each code corresponds correctly to its full name. This step prepares us to better understand and handle missing or ambiguous values in the embarkation data. Pivot tables quickly summarize data across categories. Let us create one for fares by sex and class. This line is a comment explaining that the pivot table will show average fare by sex and class. This line creates a pivot table from the data frame with sex as the rows, P-class as the columns, and the mean fare values. This line prints the resulting pivot table so we can see the average fares organized by sex and class. Running the cell now. This pivot table shows the average fare paid by passengers, broken down by sex and passenger class. Notice that first-class passengers generally paid higher fares, with females in first class paying the most on average. This helps us understand the data distribution before handling missing values, ensuring we preserve key patterns when cleaning. For real-time series, we need a date column. The Titanic set does not have one, so let us add simulated dates. We import numpy for random number generation. We fix the random seed so our results always match. We import time delta so we can adjust dates. We set a base date for April 1912. For each row, we add a random number of days to the base date. Now the date column holds simulated boarding dates. We print some names and their new date. Running the cell now. This output shows the first 5 rows of our Titanic dataset with a newly added date column, simulating voyage dates to demonstrate handling of date data. Notice how each passenger now has an associated date within April 1912, which helps us practice missing value checks and data consistency in date columns. This step sets the stage for identifying and cleaning missing or inconsistent dates in real-world datasets. You can now try resampling by date. Let us visualize how many passengers boarded each day using a line plot. We add a comment describing the plot we will create. We import matplotlib's pyplot module for plotting. We count the number of entries per date and sort by date. We create a new figure with a specified size. We plot the dates on the x-axis and their count on the y-axis. We set the title of the plot. We label the x-axis as date. We label the y-axis as count. We adjust the layout to prevent overlap and ensure neatness. We display the plot. Running the cell now. This plot shows the number of Titanic passengers recorded each day, revealing if data entries are consistent over time. Notice any gaps or irregular spikes that could indicate missing dates or incomplete records. This helps us identify where missing values might affect our data's continuity before further cleaning. A count plot helps us see category frequencies. Let us compare survival counts for men and women. This is a comment describing the visualization we are about to create. We import the Seaborn library to enable advanced plotting functions. We generate a count plot showing the number of passengers by gender, separated by survival status. We add a title to the plot to clearly explain what the chart represents. We display the plot on the screen so we can see the visualization. Running the cell now. This count plot visualizes the number of survivors and non-survivors separated by gender in the Titanic dataset. Notice the clear imbalance in survival rates between males and females, highlighting how gender is strongly linked to survival. This insight helps guide data cleaning by emphasizing the importance of retaining the sex column and considering its impact on missing data handling. Try making similar charts for P-Class or Embarked. Mini project, feature engineering. We will now create a new feature, whether a passenger was traveling alone or not. Running the cell now. We want to know if a passenger is traveling alone. This can impact survival odds. The comment notes that we are making a new column, is alone. We assign 1 if both SIB-SP and PARCH are 0, meaning the passenger has no siblings, spouse, children, or parents. We print out the columns to verify the new feature. Running the cell now. This output shows the new is-alone feature, which flags passengers traveling without siblings, spouses, or parents' children by checking if both SIB-SP and PARCH are 0. Notice how passengers with no family aboard get a 1, indicating they are alone, while others get 0. This feature helps us capture the social context of each passenger for further analysis or modeling. Let us check if traveling alone made survival more or less likely. We group by is alone and calculate the average survival for each group. Comparing these numbers tells us if being alone mattered. Running the cell now. This output shows the average survival rate for passengers who were alone, is alone equals 1 versus those who were not, is alone equals 0. Notice that passengers traveling with others had a higher survival rate, 50.6%, compared to those alone, 30.1%, highlighting that the new feature is alone captures an important relationship with survival outcomes. This insight confirms the value of including is alone in our feature set for modeling. Can you think of other features to create from existing columns? Beginners often hit errors due to typos in column names. Let us demonstrate. This comment explains a common error involving misspelled column names. Start a try block to attempt the code inside it. Try to access the DataFrame column named AEG, which is misspelled. If a key error occurs because the column doesn't exist, handle it here. Print a message alerting that the column name is misspelled and should be checked. Running the cell now. Here, the code checks for a common error, misspelling column names, by attempting to access a non-existent column AEGO instead of the intended age. The output warns us immediately, reinforcing the importance of precise column names when creating new features like traveling alone. This helps prevent bugs early in the feature engineering process. If your data is large, loading just what you need saves memory and time. The comment explains that this is a performance trick. We provide the URL as before. We use the userCalls argument to pick just 4 columns. We print a sample so we see it worked. Running the cell now. This output shows the first 5 rows of a simplified Titanic dataset containing just the columns we need for our feature engineering: name, age, sex, and survived. Notice the mix of ages, genders, and survival status, which helps us focus on relevant data and improve performance by loading only essential columns. This setup is crucial before creating our new feature to check if a passenger was traveling alone. Practice: try loading only 2 columns you care about. Ready for a quick check? Let us see if you remember the main Pandas preview function. We ask a question to reinforce learning. We get user input for the method name. If the lowercase answer is head, we praise the user. Otherwise, we provide a hint. Running the cell now. This output confirms your understanding that the .head method reveals the top rows of a data frame, which is crucial for quickly inspecting data before feature engineering. Previewing these rows helps identify key columns, like passenger info, to create new features such as whether someone is traveling alone. Want more Pandas tutorials? Subscribe so you never miss a lesson. Final recap. You explored series and DataFrames. You learned to select, clean, filter, group, and visualize data. Try applying these Pandas skills to your own datasets. Practice makes perfect. Running the cell now. Thank you for learning with us. Like this video? Subscribe to our channel for more Python and data science. Comment below, which Pandas feature do you want to master next? Running the cell now.